Assalamu alaikum. So our current chapter of discussion is about CAM design. In our last lecture, I have gone through fundamental classification of the CAMs. There were different classifications depending upon the types of CAMs or types of followers. And then we had a brief overview of the CAM profile. So the CAM profile was when you cover a 360-degree, then what the displacement being plotted on y-axis along the rotation of cam in 360-degree. And we defined the terms saying rise, dwell, where there is a maximum displacement but it's not moving. So that's like horizontal line on such graph. That's the dwell. And there is another dwell as well in a cam which could be much longer, which is after the return. So after return from 360 you will start again, so you will have rise, and also it continually goes like that. Then we had some of the definitions. Which we will use for the design of cam. So we have discussed the base circle, trace point, pressure angle, pitch angle, pitch curve, prime circle, lift or stroke. All right, then now it's time for discussion on the displacement, velocity, and acceleration. So we had gone through one of the brief overview of the displacement. So so as we discussed, so there is one part of the curve is a rise where the displacement is increasing. Then there is a dwell part, and then you have the return, and then you have another dwell. So you see there are four different steps if you look carefully. And then the velocity, of course, when it's moving up, so that you have a velocity, constant velocity. So this is one of the velocity value. And then you have dwell, zero velocity, and then you got a negative velocity. So the graph shows an equal, so it doesn't necessary that you will have similar value of velocity on rise and return. And acceleration. So this acceleration which is shown here, which is like infinity at this particular point, what does it mean? Because we are reaching the maximum velocity with no time. So when time is zero, so of course the acceleration will be infinity. Same goes here. So the velocity is dropping immediately, so no time. So that's why it's infinity. So for the return stroke is the same as well. So this is not really the case in actual cams. So then it was discussed. This is one of the modified. So you definitely need some time to arrive from zero to maximum velocity. So even if it's a quicker, but you still need some time. So when you need some time, what does it mean? It means it has some definite magnitude of acceleration. This is what is mean actually. So now you see the instead of infinity acceleration, you got finite acceleration or deceleration when you have the return. So we got one of the categories for the rise and as well as for the return when we got one of this one. So when you look at this one on the displacement curve, they look like more like a rounding off edges actually. So they are right, just like rounding off edges. All right, then because you see the follower which moves actually up and down only. So follower is moving just up and down, and it's following relatively like a simple harmonic motion. You might have seen such analysis for spring mass system when the mass is oscillating to and fro, or the pendulum. So if the linear movement is happening, this short video, which is playing the animation, is a very good way to describe that if you have the reciprocation, you actually have simple harmonic motion. So simple, so you see the curve being generated by use of this follower is following a simple harmonic motion actually. So it's creating because why we need such analysis, because it's relatively simpler to analyze the geometries if it's following a simple harmonic motion. So now we will look the cam as performing a simple harmonic motion from onward, and then we will use that to construct the cam profiles. Yeah. So we are again, we are still on the discussion of displacement, velocity, and acceleration diagrams when follower moves with a simple harmonic motion. Yeah. So this is what I was explaining. So this is one of the type where one of the way to analyze to look at the follower that's moving as a simple harmonic motion. So we will build next couple of slides based on analysis based on simple harmonic motion. All right, so the velocity and acceleration diagram shown in figure B and C. So B and C. So the top one is a displacement, the second one is velocity, and then we got the acceleration diagram. All right. Since the follower moves with a simple harmonic motion, therefore velocity diagram consists of sine curve and the acceleration diagram is a cosine curve, right? So if it's following, displacement is following the simple harmonic motion, this is like same. So this displacement is like a sinusoidal curve, right? So if it's following sinusoidal curve, then the acceleration is a derivative of velocity. So if it's sinusoidal, this will be cosine, right? So this is like ideal way of looking at the velocity diagram. And this is the cosine curve, so this is a sine curve. We see from figure B that the velocity of the follower is 0 at the beginning and at the end of its stroke and increases gradually to maximum mid-stroke. That's what we are seeing. So it starts from 0, it reaches maximum, and then start decreasing. So that's the way it follows. And on the other hand, the acceleration of the follower is maximum at the beginning. Of course, when you have the increase in velocity, so that's the point where you have highest acceleration, right? And then we have reached the maximum value because there is no further increase in velocity, so acceleration is 0 at that particular time. And same goes to the reverse. Now, you see, this has certain magnitude. So this is the maximum velocity. It has this magnitude you can determine by calculating the height, and for the maximum acceleration, because we have acceleration maximum at the beginning, and somewhere it goes to the highest, and that's the reference. So that's the zeros, and that's the maximum acceleration. So this graph is quite interesting because we here the forward, which has been following this way, the return is not as same like that. So that's why the velocity profiles is also different. And of course, the acceleration is quite different as well. So you see, because it is quickly returning back, you see this distance from here to here, this distance is larger than this distance, right? So what does it mean? This distance is more. So if it's moving constant angular speed, so the cam they move with a constant angular speed. So it takes more time to cover this distance, and this distance is done as a quickly. So that's why the acceleration, you can see the acceleration, the magnitude of acceleration, this one is lower than this one. So the return acceleration is different. So this is another application or another diagram where we see that the acceleration or the profiling of the cam does not necessarily have equal forward and return strokes. They could have different. This is what we have. We will do some couple of examples, and you will build your understanding from there onward. And one more thing here. So what we are doing actually, because it's simple harmonic motion, the follower is performing, so it's more like a sinusoidal curve, and we are splitting the sine curve, the displacement curve, in equal spacing. So this depends on when we do some problems, we will see that we are doing different methods. So here it's been divided in 8. Same goes here, so the return is divided in 8 as well. Of course, the spacing would be different because this distance is larger, this distance is smaller, but but you divide in 8 equal parts, so you have smaller boxes here basically, right? And then this one, the sinusoidal curve for the displacement is also the simple harmonic motion curve is also split in the same way in 8 different categories, in 8 different equal parts. Just hold on with your questions, because we are going to construct such curve, and you will find what actually we are doing over here. So the displacement, velocity, and acceleration diagram when the follower moves with a simple harmonic motion. Again and again, we are just talking about the case where the follower is doing the simple harmonic motion. So so the displacement, velocity, and acceleration diagrams when the follower moves with a simple harmonic motion are shown. The displacement diagram is drawn as follows. So the steps to draw this displacement diagram. How are we doing? Draw a semicircle of the follower stroke as diameter. So you draw this semicircle as a follower diameter. So this length is the stroke length from A to 8. This length is a stroke length, right? So this is semicircle follower stroke as a diameter, right? So the diameter of this semicircle, this line, is the stroke which is written here. So this is the stroke length. Divide the semicircle into any number of even equal parts. So we normally do in even equal parts. So for example, this one is being divided in 8. For example, this is 360. Of course, this is like the whole angle is being covered 360. So you divide in equal parts. So if it's 8, then you have yeah, so you got each angle is like a 60. So you add 60, 60, 60, and you will have 180 basically. Divide the angular displacement of the cam during outstroke and return stroke into the same number of parts. So first step, you do the semicircle over here, which is done. Then what you have is you are doing the return and forward. So this is outstroke, this is return stroke. So you do the outstroke same way you do in equal parts. So if you've done this one as 8 parts, so this one should be also uh, in the eight parts as well. So again, so divide the angular displacement. So angular displacement. So total, if we are doing, let's say this is the total 360 for the cam. So this is 360. If let's say it's doing, I'm just making a number. So this is outstroke. So we are saying the 60 degree of the cam out of 360, we are doing just 60 degree as a outward stroke. We are doing 40 degree as a return stroke, and there is a dwell of 20 degree, and then you have the rest over there. So there is another dwell. So once you have these three angles known, then the last one you can find out. So once we decide we have outward angle is a 60 degree, you just divide in equal parts, equal spacing. Once you have equal spacing, then you just split in the same number of sections. So it was 8 for this semicircle. This semicircle is the vertical displacement of follower. So this is done. Then we have the cam. This part is for the cam, right? The cam rotation. So this has been done also in the same equal parts. So we do the forward, outward, or return, both same number of parts. Yeah. So now let S is a stroke of follower, as it says over here. So this is the stroke of follower. Theta 0 and theta r, angular displacement of the cam during outstroke and return stroke. So this is outstroke, and then we have return stroke of the follower. So it is done in the radians, and omega is the angular velocity in cam in radians per second. So let's say the cam is rotating with the angular velocity, right? So this hole is S, right? So that's the diameter, and that's what we have done, the half circle. So semicircle we have drawn equal to the diameter of the cam, diameter of the this equal to stroke length. And then it is moving, the cam is moving with the angular velocity of cam that is in radians per second, and the time required for the outstroke of the follower in seconds would be t0. So this is for outstroke. This is analog equation for circular motions basically. Consider a point P moving in a uniform speed of omega p, right? So this is the point which is moving with omega and radians per second, radians per round. The circumference of a circle with a stroke S as a diameter as shown in figure. The point P prime, which is this one, this P prime, which is projection of point P on the diameter, execute a simple harmonic motion. So the very first diagram which I shown, so this, because the follower is just moving up and down, right? So follower is just moving up and down. So this is basically the projection of point P when it's moving. So this is the way you construct a simple harmonic motion curves basically. So the peripheral speed of the point P prime, so the P prime, the peripheral speed would be, so Vp, because it's just moving linear, so we use this Vp, which should be equal to pi s. Pi, what is pi s? Pi s is the, so s is the diameter basically, right? So s by 2 is a r, so pi r is basically that's the distance traveled, and 1 over t0. So we are just dividing with the time to cover that for outward, and instead of time we can write this in the speed as well. So because we just explain over here t0 is equal to theta 0 over omega, so you just like inverse of it, and then that's the equation. So this is the velocity, peripheral speed of point P, and then the maximum velocity of the follower on the outstroke. Same way, because you see it's just the return time, instead of that one we use the outward. So this is the outward basically. So pi omega s over 2 theta. So same equation. So this one and this one is same equation. We know that the centripetal acceleration of the point P. Yeah. So the P, this point has centripetal acceleration. Uh, I assume you know this equation. So what is this basically? So this is this velocity, tangential velocity. So v square over r. So v square, the centripetal acceleration are determined like that. Yeah, a is equal to v square over r. So this is what it is. V instead of v we have vp, and instead of r we have op. So this is distance. So the VP already determined. So the velocity we have determined in terms of is omega s and theta 0. So you plug that one and that's your acceleration. So the maximum acceleration of the follower in the outstroke is this one. So this is the same equation being written. So that's the acceleration. Similarly, maximum velocity of the follower in the return stroke. So same equation, you just replace theta 0 with theta r. So that's the return angle, return distance covered basically in terms of angle. And the maximum acceleration of the follower on the return stroke, same equation, instead of theta 0 you just write theta r. So these are the equations which are very relatively very simple equation, and they are like a standard equation has been used for simple harmonic motion, right? So we'll use these ones to find out the velocity and accelerations. Okay, in order to draw the cam profile for a radial cam, first of all, the displacement diagram for a given motion of the follower is drawn. So the very first step which we will do in today's lecture is to draw the displacement diagram. Then by constructing the follower in its proper position at each angular position, the profile of the working surface of the cam is drawn. So in constructing the cam profile, the principle of kinematic inversion is used here. So we'll use the principle of kinematic inversion. The cam is imagined to be stationary and the follower is allowed to be rotated. So we have done the kinematic inversions quite in detail. Actually, 2 times we have discussed in lecture 1 and lecture 2. So what is kinematic inversion? You do the analysis as such where you keep one of the components. So what the normal operation is, we have to, the cam is imagined to be stationary. So cam rotates, actually cam rotates, but we in this inversion we are doing cam is stationary, and then follower is allowed to rotate, but actually follower is not rotating. It's just, so this is like one of the way, because the both have relative motion, so you can do one of the way actually. In the opposite direction to the cam rotation. So yeah, so this is one of the inversion what we can do. All right, so example, a cam is to give the following motion to knife edge. So this is one of the type knife edge follower we have done in the very beginning, the knife edge follower. So the requirements are given. The outstroke during 60 degree of cam rotation. So the outstroke is 60 degree only out of 360. 12 of the next 30 degree. So the 30 degree is 12 and return is 60. So this is same. So return and forward both are same, right? So this is a little bit easier. And 12 for the remaining 210. So the all, so this is basically yeah, so 60 for forward, then you have 12 for 30, then 60 for return. It should be 360, and the remaining is basically the angle, which is 210, because total sum should be 360. So this is the 12 return 12 basically, remaining 210. All right, so this is the cam you have to plot, and then there is some numerical. The stroke of the follower is 40 millimeter. So the stroke, the S value, this is S value, and minimum radius of the cam is 50 millimeter. So the cam radius is also given. The follower moves with a uniform velocity during both outstroke and return stroke. Draw the profile of the cam when the axis of follower passes through axis of the camshaft. So these two are the conditions. So one condition, so part A, the axis of the follower passes through the axis of the camshaft, and the B condition is the axis of the follower is offset by 20 millimeter from the axis of the camshaft. Yeah, we will do first one, and then it will be easy to understand the B actually. Okay, so the steps has been explained. What you do draw a horizontal line AX 360 degree. You draw first step, you draw 360-degree line to some suitable scale, right? On this line, mark AS 60 degree to represent the outstroke of the follower. So you have 360 degree, some suitable scale, and then you do the 60 degree, sorry, 360 is out of scale, and then for the forward you do the 60 degree that's given. So you mark the 60 degree, then you got a 30 degree dwell, and then you got another 60 for the return, right? So 60 degree to represent outstroke of the follower, ST to represent dwell, so this ST is the dwell, TP is for return to represent the return stroke, 60 degree, this is also return, this is given, and then represent stroke, and PX, which is remaining 210, that represents the dwell. Then the next is you draw a vertical line AY. So this one is, you draw a vertical line which is also 40 mm to represent the follower, 40 mm, and complete the rectangle as shown in figure. So now you have this line, you have this line which is S, and that's just complete the triangle, so rectangle, sorry. Yeah, so this is this rectangle is talking about. So divide the angular displacement during outstroke and return stroke into any equal number of parts, say 6. So we are doing 6 different parts, and draw vertical lines through each point, right? So what you do in the next step, you draw, so you draw these lines, right? So we still don't have this AG curve, so you draw this line, so 6 equal lines, and draw like vertical lines. That's the parts you have decided for how many parts you have to divide. So you divide in 6 parts, so that's the lines you draw. Since the follower moves with uniform velocity during outstroke and return stroke, therefore the displacement diagram consists of straight line joining AG and HP. So AG is you connect these two lines, AG and HP, which, and the next one is this one. So this is the displacement. Yeah, so this is the displacement. So the complete diagram shown in figure AG, HP, X, and yeah, so that's the complete diagram, right? So this is the cams, this is the follower side basically. So again, the steps are, first you draw the first you draw 360 degree, then you mark the 60 degree, 30, 60, 210. So that are the forward return dwell and return dwell, and then you split up into the equal number of parts. So here it was 6, so you draw 6 lines, right? And for forward and for the return as well. And once you draw 6 lines, what you do, you just basically connect A to G. So this is the uniform velocity, that's why it's a straight line. And then you have the return, which is also uniform velocity, that's given, so you have the straight line. and the vertical was the 40 mm. This was already drawn. So this is the diagram. Next is we want to draw the cam. So you see in this design problem, you know what is the requirement of the follower to perform. This is the requirement. So if I give you the practical example, so you got the in engine application, so the valve has to reciprocate some certain values. So it goes for valve opening time and closing time, so the valve timing. We know that for how long it has to open and for how long it has to close. What should be the speed of closing and opening? Because all this depends on the engine, the piston movement and the cylinder size, because we want complete uh, removal of exhaust gases and intake as maximum as possible. So all these things design starts with the thermal design of the engine, and then once you have that one, you you are definite, you know, you're confident that these are the requirement for the cam to be done. So you are done with the cam profile. You know that for like how long the cam has to, or how long has the valve has to open. Now in this subject you will understand to perform the required function of cam, how the cam profile should be built up. So that would be the major finding from here. So the next one. All right, so next phase is we want to draw cam profile. So profile of the cam when axis of follower passes through the axis of cam. So this is part A. So we are doing this is relatively simple. So what do you do? So draw a base circle with radius equal to minimum radius of cam. So this was given. So the cam radius was given, which is a 50 millimeter. This is what you draw. So this 50 millimeter radius is this one with center O, right? Since the axis of follower passes through the axis of camshaft, so this is the knife edge follower, this one. So this is the one, is a knife edge, and you see it is passing through, the axis, so the cam axis, right? So so the axis of follower passes through the axis of camshaft, therefore mark trace point A as shown. So this is the trace point. So this is the starting point. So when it's passing, so the A actually is the starting point. So that's the trace point. Now from OA, so you have the line. So this is OA. So this is the line OA. What you do, mark angle AOS 60 degree to represent outstroke. So you mark 60 degree because this was the outstroke, right? So you draw a 60 degree and you mark this line. So you mark this line, this is 60 degree, right? Angle SOT 30 degree. So this is the dwell. So mark another 30 degree, which is this one, to represent the dwell. And TOP angle as a 60 degree once again for the return. So you draw another 60 degree, that's for return, right? So these 60, 30, 60 was taken from these values which are given in the displacement, right? And all other angles, so this all angle is 210, rest of it is the 12 actually, right? The next, divide the angular displacement during outstroke and return stroke. So divide the angular displacement during outstroke and return stroke, angle AS or TOP, into the same number of equal parts as the displacement diagram. So because we have done this one as a different six different divisions we have done, so you also divide this angle into 6. You see we are doing this as 0, and 1 2 3 4 5 6. So you have 6 for outstroke, 6 for return stroke. He's just writing the prime number so to make it different, because here we had a different as well on the displacement diagram. Alright, so now you have divided and divide and then extend those lines as well. So you extend those lines as well, right? Now what's next? Join the points 1 2 3 1 2 3 etc with the center O and produce beyond the base circle as shown. So you draw this one and beyond the base circle. So that's what it means. So each line, for example, this one and forward, this is your drawing, and beyond the base circle you are drawing, right? You keep going there. Then now set of 1B, 2C, 3D. Now where this profile will be. So for example, to locate, we want to locate the point B, because you see this is how farther it is from base circle, right? How farther it is from base circle. Where do you know this? We know from the displacement. What you do, you measure this distance, so 1B, you measure this distance and then you just mark on the line from the base circle, you mark the point. Then you go for 2, you mark the point for 2, so this one. And then you have 3, this is the distance, and you just mark on the distance as well. So this is right. So you keep doing that. So this is the distance which is required to be done, and this is the cam profile basically. So we do same thing for the forward, and then we do same thing for the return as well from the displacement diagram. The join the points A, B, C and M and B with smooth curve. So you just try to make it smooth. You see, you just connect these points, and that will give you the complete cam profile. So you see, this was a relatively easy example where building a cam profile was quite easy actually. So if you like, I can explain again. So what we have, first step was to draw the cam, the follower. And how we done it? In very simple words, you do 60, you do 360 line, the distance, and then you got the vertical follower, which was given 40 millimeter. So you draw that one, and then you mark for the 60-degree, which was given. This is the outward stroke. Then you have 12s, then you have return stroke, then the remaining 12, and then you split up in equal parts. So you draw vertical lines from the within the rectangle, and then you connect A to B, A to G. So now you would understand why we need to split actually, because we are interested in when cam is at one position, right? At one position, how much distance we need to cover. When we are at two position, then how much distance we need to cover. So that's why we need to split it up basically. So when we are definite with that one, then we can build. So with the known value of cam with the 50 millimeter, you draw the base circle, and you start from A, you mark the 60-degree for the forward, 30-degree for the dwell, and then 60-degree for the return. You do equal number of parts which you have done the deviation, so you already done. Then so you see this pink color, actually that shows the cam profile. And how we know that? So if it's a base circle, how farther it has to go up, right? So to find that, basically we are doing this distance, right? So this distance, how we are finding, we are finding from here, right? So we find from here this distance and then just mark this distance over here. So that distance will help you to find out how farther the cam has to go. Now imagine if this is moving this direction, right? So this cam is moving this direction. So this knife edge follower, it will start and it will follow the cam profile. So as we go up, 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 and then 12, it is not moving anywhere. So that's why it will stay over there. Then it comes return, and then it follows the base circle again. So that's the cam profile we have built basically. All right. So this was the case when we have cam that passes through the axis of camshaft. Now the next one. What happens if the axis is away, offset by 20 millimeter, right? So this is profile of the cam when the axis of follower is offset 20 millimeter from the axis of camshaft. So we are farther. So this is the cam center point, and this is the, so we have 20 centimeter offset, right? So 20 centimeter. But of course, the displacement curve of the knife edge follower is not changing. So this displacement curve will remain same. So we are not going to change. It's just this part which is a little bit different. So we got to start our A point not from the center which was over here last time, rather 20 centimeter apart, 20 millimeter apart from the center. So you mark this point basically. Then the steps are similar. Let's go through this. Draw a base circle with radius equal to minimum shaft cam, which is 50 mm, with O as a center. Draw the axis of the follower at distance of 20 millimeters. So you draw axis of the follower 20 centimeter, 20 millimeter from the axis of the cam, which intersects the base circle at A. Join AO. So the next is join OA. So this line, you join this line. So this is the reference actually. Draw the offset circle of radius 20 centimeter with the center O. You draw another circle also. This is this one, which is the offset circle basically, right? So from here, so of course when you have this distance is 20, so this circle when you draw, it will just like will touch this line basically. So from OA, mark angle AOS 60 degree. So now this reference line which I was telling you, you mark 60 degree. So you mark 60 degree, and then you are on this B part basically, right? And then same way you draw 30 degree. So you see you are marking on the base circle, right? But you're writing you're taking this reference angle from this OA line. So that's the major difference in offset basically. So this is the reference line, and then you have 60 degree, and then you mark, and then you have 30 degree, then you mark another line which is T, and then you 60 degree for the return, and the remaining should be the the dwell, return dwell. So now you do the same step. So you divide the angular displacement during outstroke, return stroke into the same number of equal parts. So same number of equal parts. Now from the points 1, 2, 3 and 0, 1, 2, 3 etc on the base circle, draw tangent to the offset circle and produce the tangent beyond the base circle as shown. So you same way you basically on the base circle draw tangents to offset circle and produce these tangents beyond the base circle. So basically you are from the base circle you do the tangent line. So you see this is the tangent line. You draw, you split it up in different angles and you draw these ones, right? So these are like tangents, and then they're going beyond the base circle. So you see these lines. So this is also a little different from the previous example. This is more like a tangent basically from the base circle, from the offset circle. So this is offset circle, and then extend that beyond the base circle. Now set off 1b, 2c, 3d, and this one from the displacement diagram. Join the points A, B, C, D with a smooth curve, right? So again, So this one, because this distance 1b must be this distance from the base circle. So we have drawn with reference to the offset circle, but we still need this distance, right? So this distance should be measured from the base circle, right? So from the base circle, nothing to do with the offset circle now. So 3D is this one, 3D is this one, for example, you mark that one. So that's the point. And 4E is this one, and then you mark the 4E basically. That's the way it is actually. Then you just like smooth curve, you just like you connect these points, right? And this will give you the profile. Now you can imagine if let's say you want a more accurate solution. So because what's happening between these two lines? So what you do to get it more accurate, the accuracy can be increased by splitting in even small numbers, right? So for example, instead of 6, I do it 8. So this will give even better solution to this because we will have a little bit better idea what's the distance between 2 points basically. Yeah, so we can certainly do this by finding respective points. Uh, but of course, if you want to split in more points, then it will take more time actually. Yeah. All right, so we continue with this in the next lecture.